So what does it say? Torbermite is a mineral which contains uranium. The activity of 1 kilogram of pure torbermite is 5.9 times 10 to the power 6 decays per second. So that's how many alpha particles or beta particles or whatever type of radiation it's giving out every second. That tells you how radioactive something is, how much stuff it spits out. A sample of material of mass 0.6 kilograms contains 40% torbermite. The remaining 60% is not radioactive. What is the activity of the sample in becquerels? Well, first of all, what you need to do is figure out what 40% of 0.6 kilograms is, because that's the only part of it that's radioactive. So 40% of that will give you 0.24 kilograms. So that's the amount that is radioactive. And you're really looking at your equation, activity equals N over T. So we can really say that if that 5.9 times 10 to the power 6 is for 1 kilogram, then for 0.24 kilograms, we're looking at 0.24 multiplied by that number. It's going to be a similar amount less. So its activity is equal to 0.24 times 5.9 times 10 to the power 6. Your activity is 1.42 times 10 to the 6 becquerels. So the nuclei decaying, or the amount of decays per second, is just telling you really how radioactive something is at a point in time. So if 1 kilogram has a certain amount of nuclei, obviously 0.24 kilograms is going to have a corresponding number less. We're really removing the element of time here and just looking at the fact that the number of nuclei decaying per second dictates what the activity is. So you could consider that to be just 1, because it's decays per second. So really removing that from B. And this was really the main sort of part that I wanted you to get to grips with by doing this question. The table below gives the quality factor. We know that quality factor is the radiation weighing factor. So gamma rays is 1, alpha is 20, it's the highest level because it causes the most ionization. Exposure to 150 milligrays of alpha particles for 6 hours gives the same dose equivalent rate as exposure for 8 hours to 400 milligrays of one of the other radiations in the table above. Identify this radiation. There's a few ways you can do this. I'll show you the way that I did it. You're basically looking at the dose equivalent rate being H dot equals H over T. You don't know H dot at this stage, so you need to figure out what H is for this little bit here. So 150 milligrays of radiation, remember that is your equation for dose equivalent. So you take the absorbed dose and also the type of radiation that it is. So it's 150 times 10 to the negative 6 multiplied by its alpha particles, so it's 20. We're going to use 20 here. So H gives you 3 times 10 to the negative 3 sieverts, or 3 millisieverts. We can now pop that in here and figure out what the dose equivalent rate is. 3 times 10 to the negative 3, divided by 6 will give you 5 times 10 to the negative 4, and that's sieverts per hour. Now what you're told is that is equivalent to the dose equivalent rate for the other type. So 2 ways you could do this. I've probably done this in a more complicated way. The easiest way is probably less complicated, but you can consider H dot being equal to dWr for the other type of radiation divided by T. So you know that that's 5 times 10 to the negative 4. You just calculate that out. dWr for the other one is 400 times 10 to the negative 6 times, whatever WR is, because you don't know that, divided by the time that it's exposed to, which is 8. So you get 5 times 10 to the negative 4 being equal to 5 times 10 to the negative 5 WR. Solving for WR, you'll get nothing because the pen doesn't work. You get WR equals 10. So you're going to your table here and finding which one is 10. It's fast neutron. So the dose equivalent rate is, your dose equivalent over a given length of time. That's easy enough to calculate because you can calculate dose equivalent from this equation right here. That's the dose equivalent rate is equivalent for, it's the same basically for both of these types of radiation for the dose that is received. So you're really setting two things equal to each other and solving for WR, which is 10. The remaining question that I put in there is reasonably easy. They ask you in the first part what that part is. When we go into nuclear fission and fusion, you'll get used to looking at these, but remember that number on the top there, that's the mass number, that's the protons plus the neutrons. This number on the bottom is the protons. What type of particle is emitted during this decay? It's an alpha particle, because an alpha particle is a helium nucleus, as indicated there. Part 2, more practice on this equation up here. So in this sample, 7.2 times 10 to the power 5 nuclei decay in 2 minutes. Calculate the average activity of the sample during this time. So activity is n over t, where n is your number of nuclei, is 7.2 times 10 to the power 5 divided by 120 is 6,000 becquerels. Okay, so that really contains pretty much all the equations that you use apart from absorbed dose, which is energy over mass. That's how to apply them. It's more complicated than it looks probably, but remember that activity is really determined by the number of nuclei that are decaying every second. When it talks about dose equivalent rate or absorbed dose rate, it's basically the dose equivalent or the absorbed dose over a given length of time, because how much radiation you've been exposed to, what the biological effect of that is, really depends upon how long you've been exposed to it, what type of radiation it is, and how much of the energy you have absorbed.